This is Suvarchala, working as an associate professor in the Institute of Aeronautical Engineering. As a part of transaction management concepts, in this session, I would like to discuss about the schedules of the transactions, and how the schedules are going to be defined as serializable schedules, and how to convert a non-serializable schedule into serializable schedule, or non-serial schedule into a serial schedule, by using two techniques: conflict serializability and view serializability concepts. What is a schedule? In the last session, I discussed about basic properties of transactions. What are the desirable properties of the transaction? In database management system, multiple users are going to be accessed our database simultaneously. So concurrent transaction possibility is more actually. Because of this concurrency, the transactions must be interleaved. We discussed what is interleaving of the transactions also. Because one CPU will be there and multiple transactions will be there, the transactions are going to be interleaved such that more throughput can be achieved by us. Interleaving means part of the transaction executes, then another resource may be required by the transaction, then CPU will attend the next transaction, let it be IO requirement, etc. So depending upon the requirements, the interleaving of the operations can be considered without disturbing the consistent state of our database actually. So what is the schedule? The transaction that successfully completes its execution will have commit instructions as the last statement. Various states of transactions were discussed. So after commit only, the transaction is treated as completed. Durability property also holds good actually. By default, the transaction are assumed to be execute commit instruction as its last step in general. A transaction that fails to successfully complete its execution will have to abort, and it will execute abort instruction as the last instruction. So for a transaction, the last statement may be either commit or abort, which we already explained, which we came to know during the last session as a part of the various transition states of the transaction. So the last statement of a transaction, if it commits, successfully completed. If any failure occurs, it will be aborted actually. So schedule means here, when we are having more transactions, how these transactions are executed, that is termed as a schedule. For example, the basic schedules are serial schedules. There are two transactions, let us assume that. What are the transactions? The first transaction T1 is transfer of fund $50 from an account A to transfer of fund to the account B actually. That is, transfer of fund from A to B is the first transaction. Second transaction is transfer 10% of balance from A to B. So 10%, not 50, depending upon the input, 10% is going to be transferred from A to B. These are the two transactions given by, let us assume that, two users. Transaction means, as I told you, it may be a query or it may be a part of our program, whichever the logic you are writing, in that small part can be considered as a transaction. We defined what is a transaction in the last session. So first transaction sequence of operations are read A value will be read. And also I explained you what is read-write operations. Those are not atomic operations, right? So read A is equal to, we have to subtract, because A to B transfer means subtract from A, add to the B. So A is equal to A minus 50, write A. After subtracting, we are rewriting the amount again back into our database. B is equal to B plus 50, and read B. B is equal to B plus 50, write B. Commit. This is the first transaction T1. Right? So first, if the first transaction submitted, this will be executed completely. Then the second transaction will get executed. Second transaction operations are read A, again same. We are calculating how much to be transferred as a temporary value. Temp is equal to A star 0.1. 10% no, so A star 0.1. A is equal to A minus temp, write A. Read B, B is equal to B plus temp, write B. So these are the two sets of operations in these two transactions given by T1, T2. In this example, T1 completely executes. After completion of T1, T2 get executed. This is the schedule. That is an example of, this is called as a serial schedule. Serial schedule means after completion of the first transaction, second transaction is executed. No, that is called as a serial schedule. One by one it will get executed. Right? Whenever you are doing this, A is equal to A minus 50, etc., CPU required, read-write statements, IO statements, no, those are required IO devices. But during that time, other resources are, it's not optimizable. Other resources are idle actually. When it is executing read statement, CPU will be idle. When it is executing A is equal to A minus 50 means our IO devices are going to be idle. It's not optimal utilization. Moreover, serial schedules results a lot of time taking process for certain schedules actually, certain transactions. So this is an example of serial schedule in which T1 followed by T2. Completely T1 completes its set of instructions, then T2 will get executed. Similarly, let us assume that the same transactions are another serial schedule. So a serial schedule here, T2 followed by T1. So if there are 3 transactions are there, how many possibility of transactions? Let us assume that we have T1, T2, T3. 3 transactions are there. How many possible serial transactions are there? T1, T2, T3, T3, T1, T2 and T3. So when you are using this schedule transactions, 3 transactions are there, T1, T2, T3. What are the possible serial transactions actually? T1, T2, T3, T1, T3, T2, T3, T2. Similarly, T2, T1, T3, T2, T3, T1, T3, T1, T2, T3, T2, T1. These are the various possible orders. Right? So, it depends upon the transactions which we are. 3 factorial possibilities are there for us. So, even n transactions are, n possible serial transactions are possible actually. In a schedule. Schedule means in a period of time, number of transactions submitted to your system actually. So these are all the order. Order may be anything, but all these are processing after completion of one transaction, another transaction is get executed. No, these kind of transactions are known as serial schedules actually. Now, if the serial schedules are executing, then there is no any inconsistency in our database actually. We are assuming that all our transactions are leaving our database in a consistent state so that any serial order of these transactions will leave our database in a consistent state only. No problem actually. Let us consider 2 transactions, previous 2 transactions in which the instructions are interleaved. The following schedule, this is a schedule, is a serial schedule but is equivalent to schedule 1 actually. It is not serial because it is not at all completing the first one. Part of the T1 completed, then T2 started, part of the T2 completed, CPU shifted to T1 and so on and so forth. Now just observe here, only first 3 instructions of transaction 1 are executed, then CPU handles the next set of instructions of T2 and some instructions of remaining instructions of T1 and remaining like that. That means it need not be only 2, it may be interleaving can be done in any way actually. This is not a serial schedule, strictly speaking, but we will check whether it is possibility of equivalence of the serial schedule or not. Any serial schedule. As I told you, n factorial serial schedules will be there for n transactions. Among them, if such transactions, interleaving of the operations are there, if such transactions are going to be converted into or equivalent to any of the serial schedule, then also that kind of schedules also leave our database in a consistent state. That is, correctness will be there. You consider this another schedule here. Here also interleaving there, but this schedule may not be equivalent to serial. How can you say? We discussed in the previous session also. How can you assure the consistenciness? In the as a part of the acid properties, consistency will be assured based upon certain constraints we are going to impose, explicit constraints. In this example, before transaction, after transaction, sum of the accounts must be equal. If the sum of the accounts are equal, then any type of schedule results our correctness or a consistent state of our database. But in this example, in the schedule 4, the preservance of A plus B, that is sum of A plus B, is not at all possible. Take some example of A and B. A is having 1000 rupees and B is having 500. So before transaction, what is the sum? 1500. Okay. When we are after any transaction also, because transfer of fund only, no, we supposed to get 1500 only. First transaction, after first transaction, T1 is subtracting 950 and 500 plus 50, no, 550. Then it is equivalent to again 1500 if it executes in a serial order. T2 means here 950, 10%. 10% means 95 is going to be subtracted. After 95 subtraction, 855 will be there. And 95 is added, 545 will be there. Again, sum of the two values will be 1500. So, if in any schedule also, if you are able to get after completion of the two transactions, the sum of the A and B are equivalent to 1500, yours is equivalent to the serial transaction. But in this current schedule, you observe we are subtracting A, then it is reading. That means after 950 is read, on 950 percentage calculated and it is subtracted again, it will become as a 855. And we are writing A, then we are reading B. So we are writing A means A will be 855, it's okay. But we are reading B means by that time, what is the B value? 500 only. So after writing A, again we are writing A in the second one. A of the first transaction is 950. This 855 becomes again 950, which is not a consistent one. So that means the transactions which have simultaneous concurrent transactions are there. That is, interleaving of the operations are considered. In such cases, we have to check explicit constraints are satisfied or not, so that the consistent state can be checked by us actually. So that's why any interleaving of transactions are there, then we have to consider whether those are serializable schedule or not. What is serializable schedule? What is serializability? Serializability means each transaction preserves our database consistency. Each transaction preserves our database consistency. That is the basic assumption. That means every transaction is a correct transaction. It leaves our database in a consistent state. So that's why serial execution of these transactions, any number of transactions, such transactions will leave our database in a consistent state. That is correct state. Each one of them is consistent means a serial order of this transaction also will result in consistent state of our database. Correctness will be there. Because each transaction leaves correctness independently, so that's why individually and one by one we are doing, no? So a serial schedule also leaves our database into a consistent state only. That is correct state only. But schedule. Schedule means multiple transactions are executing simultaneously by using concept of interleaving transactions. Then whether that particular schedule is leaving the database consistent state or not, we have to check. How to check? If any concurrent schedule is leaving or can be converted into equivalent serial schedule, then that particular schedule is known as serializable schedule. That is, any interleaving operations or any concurrent transaction schedule is known as serializable if it is equivalent to any one of the serial schedules. Various number of serial schedules are possible, no? As I told you, 2 transactions, 2 serial schedules. 3 transactions, 3 factorial, no? 6 serial schedules. N transaction means n factorial serial schedules will be there. Combinations, order of the transactions to be get executed. So any concurrent transaction leaves or can be converted into equivalent of any serial schedule, then that particular schedule is known as serializable schedule. So that means serializable schedule leaves our database into a consistent state actually. So we have to consider any concurrent transaction schedule is there. We have to check whether that is equivalent to any one serial schedule or not. If you are able to prove it is equivalent to serial schedule, then automatically that schedule is serializable schedule which leaves our database in a consistent state actually. There are 2 techniques are there to check such type of concurrent schedule is equivalent to serial schedule or not actually. So conflict serializability, we will term it as view serializability. By using these 2 techniques, we can verify any concurrent transaction schedule is serializable or not actually. So the serializability checking can be done by using these 2 techniques. When we are using these transactions, let us assume that T1, T2, we have done previous cases. The main operations we are related to database only we are thinking of. So we are not considering the all other resource management as in case of operating system. We are all now thinking of how to make our database in a consistent state after completion of all these concurrent transactions also. So that's why related to database, only read-write statements are related to database directly. All of the remaining statements are executed in the buffer only. We are taking the data from database, secondary storage device by using read statement. We are rewriting the data into database by using write statement only. The remaining operations are related to our CPU directly, which are done in the buffer only. Those are not directly related. So that's why the transaction length can be reduced or simplified transactions can be considered by ignoring the other operations. We will use only read-write operations only and we will consider only read-write operations by ignoring all other operations. Whatever the updations are, logical verifications have done in our transaction, those are all in the buffer only. So that's why those things we won't consider. We assume that transactions may perform arbitrary computations on data in local buffers only, in between the read and write statements. Right? They may be there, but transaction processing concept, when we are verifying them, we will consider only those 2 operations only. So our simplified schedules consist of only read and write operations. Simplified schedules consist of read-write operations. Between each read and write pair, maybe multiple other operations will be there that we are not considering because all of them are done in our buffer management. Now we'll move to the first technique, conflicting serializability. For conflicting serializability, first we have to understand what is meant by conflicting instructions. So as a part of that, conflicting instructions means we will consider 2 instructions. These 2 instructions are conflict or not. The instructions LI, LJ, 2 instructions, which belongs to 2 different transactions, TI and TJ. Let us assume that we are taking 2 instructions. One instruction from one transaction, another instruction from another transaction. That is Li from Ti, Lj from Tj. These two instructions are said to be conflict. When these two instructions are said to be conflict, if and only if these two instructions are performing some operation on the same data item. If they are different, no need to check at all conflict. If the instructions are on different data items, they are doing some operation on different data items, automatically those instructions are non-conflicting instructions only. But if they are both are existing on some data item, same data item, that is same data item is accessed by both instructions and at least one of them is a write instruction, then we will say Li and Lj are conflict instructions. So as I explained you in the previous slide, the instructions are only read, write only we are considering. So Li, Lj are two instructions on same data item. This is only same data item are there. Then only conflictness will be checked. Otherwise, we can say that those two instructions are non-conflict instructions. So in this queue here, possibilities are there, no? Li may be read, Lj may be write. This may be write, that may be read. Or both are read, or both are write. These are the four possibilities are there. So Li is read queue, Lj is read queue. Li is read queue, Lj is write queue. Or Li is write queue, Lj is read queue. Or both are write. What is definition? Both are conflict instructions if any one of them, at least one of them is write instruction. Yes. The first condition satisfies because both instructions are on queue only, same data item. But in first case, both are read. So that's why these are not conflict, don't conflict or non-conflict instructions. But these three pairs are, in each of these cases, write instruction is there. One of them is write instruction. So those are all three are conflict instructions. Conflict instructions means we cannot interchange. So conflicting instruction means here a conflict instruction between Li, Lj forces a logical temporal order between them. Temporal means time-wise. That means if Li is initial, first occurs in the first transaction, Lj occurs in the second transaction after Li, the order must be maintained by us if both are conflict. Temporal order, logical order must be maintained by us. That means Li occurs before Lj, then we cannot change their order. But if those are non-conflict instruction, we can change their order. That means the conflict between Li and Lj forces us to maintain the temporal order between them. That is, the order of the instructions should not be changed. If Li, Lj are consecutive in a schedule and they do not conflict, non-conflict instructions are there, their results would remain the same even if they are interchanged. Even they are interchanged, their results are going to be remains same even after interchanging in the schedule. That is, Li before Lj is there. Lj, Li can be interchanged. Temporal order can be changed if both of them are non-conflict instructions. But conflict instructions, you cannot interchange. The order must be maintained by us. Right? So, two instructions are conflict instructions if both operations are belongs to the different transactions. First case. Second case, both operations are access the same data item. And the third one, at least one of the operations is a write. Then we will say those two operations are, or two instructions are conflict. Two operations are conflict if changing their order results in different outcomes. So that's why they should not interchange, or we should not disturb their temporal order. So two operations are conflict if changing their order results different outcomes. So that's why those instructions, temporal order must be properly maintained. So read-write conflict will be there or write-write conflict will be there. What is conflict serializability? If a schedule S can be transformed into a schedule S dot, a given schedule S was given. If we able to transform this schedule S into schedule S dash, another schedules, by a series of swaps of non-conflicting instructions. As we explained in the previous slides, if the two instructions are non-conflicts, they can be interchanged. They can be swapped. The order can be swapped. So, if we able to get a schedule S dash from a given schedule S by applying a series of swapping of non-conflicting instructions, we will say S and S dash are conflict equivalent. That is, we able to get S dash which is conflict equivalent to S. Then the schedule S is conflict serializable if it is conflict equivalent to any serial schedule. That means if S is a schedule and if I able to get S dash a conflict equivalent schedule where S dash is one of the serial schedules, then I'll say S is conflict serializable. So what is conflict serializability? From a given schedule, if a new schedule S dash able to generate by using series of non-conflict instructions swapping, and that S dash is newly generated S dash, which is a conflict serializable schedule. S dash is equivalent to our schedule of respective serial schedule, any one of the serial schedule, then we will say S is a conflict serializable. That means if S is a conflict serializable means it leaves our database in a consistent state because it is able to generate equivalent serial schedule by using conflict equivalent process actually. For example, we'll consider here two schedules, schedule 3, schedule 4 of the previous transaction only. Let us assume that as I told you, simplified transaction representation. As a part of the simplified transaction representation, we are using only read and write statements. So read A, write A, read A, write A, read B, write B, read B, write B. In between, multiple operations are there. This is same as the schedule 3 which I have given to you previously. This is a simplified form of the schedule 3. Now, this is not a serial schedule because the transactions are not executing serial order. This is if you are specifying like this means temporal order means this is first unit 1 time, unit 2, unit 3, unit 4, unit 5, unit 6, unit 7, unit 8. If you are taking as order means it's first, second, third, no, that order is indicating, let us assume that in terms of the time. Now, any swapping can be applied or not, that we will see now. So, any swapping means, for example, two instructions belongs to two different transactions must be considered. So, that's why possibility is, I may consider this and this, or I may consider this pair, I may consider this pair. Two instructions of different transactions of the consecutive. Consecutive means order-wise, after one instruction, other instruction must be there. For example, if I am considering write A and read B, so read A of T1, T2, this is first one. This pair can be checked whether these two instructions are non-conflict, I can swap. But what is the condition first? Both instructions are on same data item? Yes. But one of the instruction is write statement. So that's why these two instructions are conflict instructions. These two instructions are conflict instructions. So I cannot swap. That is, I cannot interchange. Fine. Then what are the next consecutive pair? This is the next consecutive pair. This is first consecutive pair, second consecutive pair. So the first pair is not possible. Why? Because it is the pair is conflict instructions. Considering the second pair, write A and read B. Both are on different data items. And both are on different data items means I did not check read write also. Different items means automatically those two instructions are non-conflict. These two instructions are, the pair of these instructions are non-conflict. So non-conflict means this order can be changed. So this order can be changed means this will become as a third instruction, this will become as a fourth instruction. These are interchanged. Temporal order was interchanged. That means what is the order I will get? Read A, write A, read A, then read B, write A. So as a part of that, after interchanging, we will get this read will become as a third instruction. For fourth instruction, this will become as a here, fifth, interchanged. After that, what happens? Write B and this, here it will come no, write A, write A, write B. These two are consecutive instructions. So write B, write A, both are on different data items. Again we can interchange. So when I am going to interchange, I'll get write A here. Then I'll go read B. Read B, read A, write A will come here. Before this. This will come down. Then again read B, read A can be interchanged because on different data items. Again write B, read A can be interchanged on different data items. We will get this. So totally 4 conflict instructions have been 5. Totally 5 conflict instruction, non-conflict instructions have been interchanged so that we will get a schedule of 6 actually here. So whenever we are doing this, that means it is a non-serial schedule, and non-serial schedule by applying series of interchanges of or swapping of instructions of non-conflict instructions, we able to get this one of the serial schedules, T1 followed by T2. Then the schedule 3 is a serializable schedule. So what is serializable schedule? This serializable schedule is leaving our database in a consistent state which is equivalent to one of the serial schedules. So that's why it is leaving into correct state of database actually. So that's why schedule 3 is equivalent to schedule 6, that is conflict serializable schedule 3. Therefore, we can say that that schedule provides us correct database. Another example, T3, T4. T3 is having read queue, write queue. T4 is having write queue. This schedule is conflict or non-conflict relation. Conflict means here, these two. Is it possible to interchange? Both of them are on same data item. One of them is read, one of them is write. So I cannot swap. Similarly, this is another possibility. Write queue and write queue of T3, T4. Those are also not interchangeable. That means from this schedule, current schedule, I am not able to find equivalent serial schedule. That is T3 followed by T4 or T4 followed by T3. That means I supposed to get read queue and write queue, then write queue of T4 or write queue, read queue, write queue of T3. I'm not able to get by using series of conflict instructions mapping because here there is no possibility of interchanging the instructions here. So if there is no possibility of changing order cannot be able to change and we may not able to get an equivalent serial schedule. This schedule is known as non-conflict serializable schedule. That is, we are unable to swap instructions in the above example and either the serial schedule T3 followed by T4 or T4 followed by T3 cannot be resulted. So that's why the above schedule is non-conflict serializable schedule. That is possibility of any inconsistency of database may arise actually. How to check whether that particular schedule is conflict serializable or not? To check a given schedule is because converting many number of transactions will be there. For just the purpose of explanation purpose, we are taking only 2 transactions. But in real-time applications, there may not be only 2 transactions. Schedule means in a prescribed period of time. In this particular time, n transactions will be there. How can you find equivalence of these n transactions into one of the serial schedules? So a little bit tedious task. So that's why there is a technique to check whether a given schedule is or any schedule is conflict serializable or not. If it is conflict serializable, we can say it is leaving our database in a consistent state, no? So that's why how to check it. A precedence graph technique is there. By using this technique, we can check whether the given schedule is serializable or not actually. So what is precedence graph? Precedence graph is a direct graph where the vertices are transactions. Graph means vertices and edges will be there. So that's why where the vertices are transactions and edges. Edges means arcs. So what are the arcs? We will draw an arc from Ti to Tj. We will draw an arc from Ti to Tj if 2 transactions conflict. 2 transactions conflict means Ti accessed the data item on which the conflict arose early. That is, Tj was written. That is, we are able to draw an arc by the item that was accessed. Draw an item was accessed which was written by the another transaction, which was updated by the another transaction. We are able to write that particular data item on that particular arc also, so that that arc is related to the conflict instructions of that on a particular data item. So like that we have to draw a graph, precedence graph we will draw. After drawing precedence graph, we have to check is it acyclic or not. Acyclic means there should not exist a cycle in our precedence graph. If our precedence graph is acyclic, then the respective schedule is conflict serializable schedule. That means it is acceptable schedule. It will lead to an equivalent serial schedule also. So, how to check cycles? Acyclic means there should not exist a cycle. Checking of a cycle in a graph is various algorithms are there. The basic algorithm will take n square time depending upon the n number of vertices actually. Even if you are considering edges, then it will be n plus c also. Better algorithms are also available. So that's why we able to first understand whether graph is going to be drawn or not. Once the precedence graph is drawn, and we have to verify whether it is acyclic or not. If it is acyclic, then the respective schedule is considered to be as a conflict serializable schedule. Once the graph is acyclic, the serializability order easily can be obtained by using a topological sorting technique on graph actually. That's why if you able to draw a graph, then automatically checking an acyclicness result into a serializable schedule actually, equivalent serializable schedule. So how to check conflict serializability? For each transaction Ti participating in a schedule S, create a node labeled Ti in the precedence graph. N transactions are there, N nodes will be there. Okay. For each case in S where Tj executes read f of x, after Ti executes write of x. Ti executes write of x, after that Tj executes read of x, then there will be an edge from Ti to Tj. That means wherever it writes from that particular node to wherever it uses after writing to that node, an arc will be drawn actually. For each case in S where Tj executes a write x, after Ti executes a reading, combinations, 4 combinations will be there, right? So after reading, another one is writing, then there will be again edge from reading to writing. That is Ti to Tj. Right? So, another one is Tj executes write, after executes write, both are write, then Ti to Tj. Before which one is done, from that to after it is going to be done, from that node to the before execute. That is Ti executes a write statement which was written by the Tj already. So that's why from Ti to Tj there must be an arc. So when you are using the Tj executes a write statement after Ti executes, after no, so from whichever is the first write is there, from there you are going to write. In the previous case also, Ti executes after Ti executes a read statement. So wherever the initial one, from there you are going to starting the graph to the other one actually. So each case of yes where Tj executes a write after Ti executes a write statement. After drawing such a graph, the schedule is S is a serializable schedule if and only if the precedence graph has no cycles. For example, a schedule was drawn like this. T1, you are having Ti, Tj, Tk, Tm, and this can be drawn acyclic. How can you check here? You can start from Ti, you are having Tj, then you are going to have Tk, then you are going to have Tm. We can convert into acyclic graphs. Another example was given here. Schedules are there. You observe T1 schedule, T2 schedule. Here we are reading X. T2 is reading X. And X item was written by T1 already. So after writing by T1, T2 is reading. After reading Y, then it is writing again. X is and reading and writing after completion of the T1 transaction. No? So from T1 to T2 on X we are drawn. You observe the second schedule. Here T2 is writing an item X. After that reading is going to be done by T1. So that's why from T2 to T1 there is that is whichever is done earlier, from there the arc starts to the transaction immediately which transaction is using it for reading or writing purpose. You observe the interleaving transactions here, that is concurrent transactions. T1, T2 are there. Here, read item X. X is equal to, you are going to have some value, and you observe here on X item, read was done by T1, then read was done by T2, second. So before T1 is starting, T1 to T2, X was, there is an arc because initial reading was T1. After that, T2 read the X value, no? So from T1 to T2. Another data item is there, Y. Y was read by again T1 and it was written, Y was not used by T2 anyway. But X item, another one is write was done by the T1 and write was done by T2 also. But the first was done by T1. Again, we are going to have from T1 to T2. You observe the second one, write was done in the second one, T2. Again, write was done in the previously done by T1. So T1 to T2 is there. This graph is precedence graph for schedule C is having a cycle. The schedule C is having a cycle here, forming a cycle. So it's not a serializable schedule. Coming to the next one here, write is earlier T1, read is by T2. So T1 to T2 X, write earlier X, but which is not done by anything by T1. X was after writing, there is no X reading or writing in T1. So there is no other arc. This is a serializable schedule. A precedence graph doesn't have any cycles. So the schedule D is a serializable schedule. Right? So we have to consider such type of serializable schedule is used for concurrency control. The schedule was being different schedules able to generate for concurrent transaction, and by using this conflict serializability test, we able to check the concurrent transactions are executed properly or not actually. Database management system enforces a set of rules to ensure serializability. Those rules are going to be based upon our conflict serializability, and many other techniques are there actually. Without giving any correctness, it is very difficult to test the serializability in practical. So we have to consider, along with checking system load, time of the transaction submissions, and priority, any priorities were given, so that the ordering can be done by us properly operations. So by using these serializable schedules, concurrent transactions correctness can be ensured by the database management system by enforcing certain rules and regulations. Thank you for watching this video. I'll discuss about view serializability the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.